Okay, we're connected. So let's start. Consider the series. We have the infinite sum, the sum from n equals 0 to infinity of 1 over 2n. Part 1, let's expand the series. By expand the series, I want to write out the first several terms and look at the pattern. I'm not very good at knowing a pattern until I start like plugging it in and seeing what it looks like. So when I plug in 1, my first term, I'm sorry, not when I plug in 1. My first term, I plug in 0 because it starts at n equals 0, right? So I plug in 0, 2 to the 0 is 1, and I get 1. My next term is 1, 2 to the 1 is 2, so I get 1/2. My next term is 2. When I plug in 2, I get 1 over 2 squared, which is 1/4. Or I could think about this as the infinite sum from n equals 0 to infinity of 1/2 to the nth power. 1 to the n just equals 1. That's why they can move it to the denominator. But I could think about it as I'm multiplying by 1/2 each step of the way. So my next term is 1/8. My next term is 1/16. I keep going, right? If your series ends, you would want your last term to be the ending. So 1 over 256. If your series doesn't end, you want to leave the dot, dot, dots at the end so it indicates that it goes on forever. Okay, so let's talk about what do the individual terms converge to. Converge to means as I get to infinity, if I were to just take those numbers and look at what they're doing, where are those numbers going? Are they blowing up and getting infinitely bigger? Are they approaching a single value? What is happening as those individual terms are moving on? Take 30 seconds to talk to your teammates. What's happening to those terms? All right, let's channel first semester. As I plug in infinity, which I know we can't do, but as we think about plugging in infinitely large values, the top stays the same and the denominator gets really big. It keeps getting big. And 1 over infinity evaluates to 0. Please note my arrow notation. This is one of the things that they get really fussy about. If you put that the limit equals 1 over infinity and 1 over infinity equals 0, they think it's a linkage error. I know that you know that 1 over infinity doesn't actually equal 0. It's just approaching 0. But they think you think it's actually equal. Okay, what is the ratio between the terms converge to? So the formula for that is the limit as n approaches infinity of a of n plus 1 over a of n. So let's use this formula right here. So we have the limit as n approaches infinity. Before I even use that formula, do you already know? Anybody? Yeah, we talked about it when we were making our series in the beginning. I said, oh, you can rewrite it, and every step you're multiplying by 1/2. If you're multiplying by the same thing, that's your common ratio. Okay, so a n plus 1 is 1 over 2 to the n plus 1. and an is 1 over 2 to the n. And I'm looking for the limit as n approaches infinity, and we're going to do some complex fractions. Everybody's favorite. I will rewrite this as multiplication by the reciprocal. 1 over 2 to the n. Oh, and I'm going to split these up. Times the reciprocal to the n. Oh, where's my n going? Is everyone okay with what just happened? Cool. Now I have a 2 to the n in the numerator and in the denominator. Those cancel out, and I just get the limit as n approaches infinity of 1 over 2, which equals 1/2. Bless you. What does the sum converge to? Oh, here we go. This is the sum that we didn't remember. I'll give it to you. So the sum for an infinite geometric series is a sub 1 over 1 minus r, where r is the common ratio. And a sub 1 is the first term. And I'm sure you've heard this before, but it bears repeating. When I am using all these little numbers next to the A's and the N's and things, they are a subscript. They are like below grade, below the line. It's not A with the 1 next to it. It's A with the 1 down and to the right. I know sometimes my handwriting's a little sloppy, but that's what it's supposed to be. Okay, so let's see if we can find the sum. We knew that there is a common ratio of 1/2, so we know that the common ratio is 1/2, and we know that the first term is 1. So my formula is 1 over 1 minus 1/2. So the sum is 2. How are we feeling? It's all coming back? It's like riding a bike. Let's keep going. So in question 1D, we asked if the sum converged. There are many tests for the convergence of a series. We're going to perform the following convergence tests. There is a cheat sheet. It is at the back. So if you go all the way to the end of the packet, there are some handwritten photocopied pages. So this is a flow chart for your convergence tests. And this sheet right here, I think you're going to reference a lot. We will go through and learn what all of these are, but these are all the convergence tests for series. And yes, you're supposed to have them memorized. So we have those, and we're going to reference back to that, okay? Some of them we actually already know. Some of them we're learning for the first time. We're going to practice using them. They're all different ways to test if a series converges. Okay, so first one we're going to do is partial sums. The way partial sums works is you look at all the different partial sums. So the sum of the first term, the sum of the first 2 terms, the sum of the first 3 terms, the sum of the first 4 terms, and you see if there is a pattern so that those sums are approaching a single value. And that's how you would know. So our first sum, our first partial sum, S1, is just the first term. Our second sum, S2, is 1 plus 1/2, 3/2. Our next sum, we have all of our previous stuff. So 1 plus 1/2 plus our next one, 1/4. So 3/2 plus 1/4, which is 6/4 plus 1/4 is 7/4. Our next sum, 1 plus 1/2 plus 1/4 plus 1/8, sorry. So 7/4 plus 1/8, 7 times 2 is 14 plus another one. So I got 15/8. My infinite sum, have I come to a conclusion? Has it settled down into a pattern? Can I see where it's going? It's getting bigger each step, but it's slowing down a little. Like, I can't really tell. I don't know. I'm not sure. I'm going to say this is inconclusive. We already know that it converges to 2. And so it hasn't broken that rule. It just hasn't proved to us that it actually gets to 2. Right? Let's look at a geometric series. So the geometric series test says if it's a geometric series, we know it converges. So we can find the infinite sum of a geometric series by using our formula a1 over 1 minus r. And we found it. This is just the formula we did from up above. As long as the common ratio has an absolute value that is less than 1 and the series is geometric, we know it converges. So at the end of the day, I think that's the test that I used to say that it converged, right? Let's try another one. We have something called the nth term. If the nth term converges to a value, here, I'm hopeful that you guys are flipping back and forth and looking at it, but let me get there as well. This is the nth term test, okay? So if we have the sum of a series, the sum of a sequence, if we have a series, if the limit as n approaches infinity does not go to 0, we could know that it diverges. It's only good at showing me for something that diverges. It is no good at telling me that it converges. But it's helpful because, one, it's a real easy test, and it eliminates the ones that diverge, so you don't have to keep doing work, right? If it diverges, I can say it's divergent, and I'm done. I don't have to do any more math. But it's inconclusive. If it goes to 0, it might converge, it might diverge, we don't know. So in the problem that we're looking at, I'm going to keep flipping back and forth. Actually, I have a better idea. Watch this. Look at how smart I am. Duplicate. We're going to put, no, not there. Aha, look at this. Okay. Now we can see both. Oh, look at, I love when technology works for us. Okay, so we were looking at our nth term test, and we are testing to see if the limit as n approaches infinity equals 0 or not. It's only good to tell me if it diverges, but it is a useful test, and it's almost always the first one I do. So the limit as n approaches infinity of 1 over 2 to the n, we did this up above, right? We said it approaches 1 over infinity, which approaches, not equal sign, come on O'Connor, which approaches 0. So this is inconclusive. If it didn't get to 0, it would diverge. But it does, so maybe it does converge. The next one is called the ratio test. Here's the ratio test right here. I like this one a lot. Doesn't always work, but what you're doing is you're finding a ratio of the next term to the current term. So you're looking at the limit of the ratio. So I'm going to put a n sub n plus 1 over a sub n. And then I'm going to compare what those two values are. So the limit as n approaches infinity of the absolute value of 1 over 2 to the n plus 1 over 1 over 2 to the n. We already spent a lot of time figuring out what that equaled, right? Oh, is this one the reciprocal though? No, we figured out this formula for the ratio. We already did that up above. We know that that equals 1/2. So let's check out the rules. It converges absolutely if that limit is less than 1. So this L is the limit, is less than 1. Since the ratio is less than 1, it converges. It diverges if the limit is greater than 1 or if the limit is infinite. I'm reading right here. It's inconclusive if that ratio equals 1. But since it's less than 1, we get to know that it converges. Yeah.
Is for this one, is it the absolute value of the ratio or just like the ratio itself?
It's the absolute value of the ratio because it could come out, if it comes out to be like -5, that's less than 1, but the ratio is not less than 1, so it's not going to work.
Okay.
Right? Or the absolute value is not less than 1 is what the words came out wrong. Words salad. Okay. I want you to repeat this process with your teammates for question 2. So consider the series, expand it, do the terms converge, what's the ratio, is it geometric, do partial sums, okay? And then we'll regroup as a class. Normally I would make you do this as board work, but I feel like it's useful for you to have this on paper. Would you agree?
Yeah.
Okay, so we're going to do it on paper, but I want you to think about it as if we were doing this as board problems, okay? So working with your teams, give it a whirl. How many teams are on number 3? How many teams are on part E? We're on part C. Okay, keep going. I want you to do 2 and 3.
Okay.
It would, so if I had had more time to rearrange all of this stuff, I would have had this be a bunch of board problems, and then we would have done some consolidation at the end. But as it is, we're doing it with our teams. There's paper notes right there if you want it, and no, that's not where I want it. There's digitals in Schoology, and I recorded the first half, so it's there for if you need it. It's actually still recording that whole conversation. Wrong thing. How we doing? This is the most interesting problem on the page. So what happens if you're looking for a limit, and the limit's approaching infinity over infinity? We have a tool for that. Do you remember what we tell? You can take the derivative of the top and the derivative of the bottom, and then test your limit again. Yeah. Let me go back to the beginning. What is the ratio converge to? So the ratio would have been, I would have condensed this, because you can't cancel those because of the addition. This is n plus 1 over n plus 4. I wouldn't multiply it out because if you have it listed like that, here. I think we're ready to talk about these. I'm going to put them up on the screen. So if you have it written out, I feel like, okay, this part, fine. This one we got inconclusive, yeah. Let's look at this ratio test, okay? So I did a little simplifying for my n plus 1. I got n plus 1 over n plus 4. And when I look at that and I multiply that out, I could FOIL out the whole thing, but that's going to waste a lot of time that I'd rather be using on calculus. I know that if it's balanced, n squared over n squared, all the other terms don't matter. And I look at the coefficient, 1n squared over 1n squared, it approaches 1. Which is inconclusive. We don't know if this converges or diverges. It wasn't geometric. It doesn't have a common ratio. When I looked at my partial sums test, I can show some of these sums, but it's not going anywhere for me right now. So I can't really see what's happening. So for that whole one, at least right now, without using more tests, it's inconclusive. I don't know what's going on with this. I have not proved that it converges or diverges. I would need to do some other tests to figure it out. Okay, let's talk about 3, and then after 3, we'll take a brain break. So I expand the series. which was interesting because we're squaring on the top, right? 1, 4, 9, 16, 25, 36. And then we are doing powers of 2 on the bottom. 2, 4, 8, 16, 32, 64. In my brain, sometimes it's easier to do all the numerators and then all the denominators because I'm not switching between the two patterns. So sometimes that's how I fill it in. It's up to you how your brain works as long as it's organized and legible. And I like to keep my fractions like 4 over 4 because it helps me see patterns. I know that equals 1. I could have written it like 1. But I was acknowledging that it was a pattern. And the pattern does some crazy things at the beginning, right? We've got 1/2 plus 1, 9/8 is bigger than 1, then it goes back to 1, and then they start getting smaller. So by expanding the series, I'm already seeing, as I keep getting bigger, I'm noticing the fractions will keep getting smaller, but at the beginning of this, they're doing some other stuff. Okay, so I started doing my partial sums. It is not settling down for me. It's kind of all over the place. Partial sums test is good to know how to do, but it's not usually going to be the one that you're using, but it's a good skill to have. So perform the nth term test. This is the most interesting problem on the page. So the nth term test says, what's the limit as n approaches infinity of my terms? So infinity squared over 2 to the infinity approaches infinity over infinity. That looks like it's going off into the sunset. I don't know how to evaluate that, except we have a tool. Way back in first semester, we learned L'Hopital's rule that said if you have an indeterminate form, you can take the derivative of the numerator and the derivative of the denominator. Thank you. There's paper copies here if you want one. You can take the derivative of the numerator, the derivative of the denominator, and then try again. So that's what I did. In case you forgot, the derivative of 2 to the n is 2 to the n times the natural log of 2. The derivative of 5 to the n is 5 to the n times the natural log of 5. Actually, the derivative of e to the n is e to the n times the natural log of e. It just so happens that the natural log of e equals 1. In case you never noticed that. That one also came out in determinate form, infinity over infinity. So I L'Hopital'd it one more time. And then the last time, 2 over 2 to the n times natural logs of 2 squared gave me 2 over infinity. That approaches 0, which is great. It doesn't diverge, but it's inconclusive. I still haven't proved that it converges. All right, last one was the ratio test. I start not wanting to make giant fractions, so I start writing them as multiplication by the reciprocal at some point. But I am doing a giant fraction. I'm dividing the two big things. It's just easier for notation purposes to kind of write it as multiplication by the reciprocal. So get used to seeing that. As I'm going through, I'm trying to simplify and hope that this comes out nicely. So I had n plus 1 quantity squared over 2 to the n and 2 to the 1. My reciprocal of the other term was 2 to the n over n squared. The 2 to the n's cancel, thank goodness, because that's part of what was giving me all kinds of problems. And again, I see that it's balanced. N squared on top, n squared on bottom. When it's balanced, I look at my coefficient. My coefficient is 1/2. Now, this is really important. The ratio between the terms is 1/2. The series does not converge to 1/2. In order to figure out what it converges to, we're going to have to do some other stuff. Okay. Pausing the recording. We need a brain break.